Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, as you know that since our previous sessions we have been talking a lot on nucleophilic substitution reactions. Dear friends, in this lecture also we are going to talk on nucleophilic substitution reactions, basically in alcohols and ethers, and for this we have again with us in our studios Dr.Aprjita Chauhan. Dr.Aprjita Chauhan is Associate Professor in Department of Chemistry, Sri Aurobindo College, University of Delhi. So dear friends, I would like to say hello to our expert once again. As I always say that she makes her lectures very lively, because the way she used to deliver her lectures with ample of examples by explaining you number of series. I hope that this session is going to be one of the most finest sessions, and she is going to deliver her lectures with ample of examples once again. So I would like to welcome our guest, Dr. Aprjita Chauhan. Dr. Chauhan, welcome to this lecture.
And I hope this lecture would be interesting for the students, and with the help of this lecture they should be able to solve reactions related to nucleophilic substitution reactions. So in our last few series that we've been conducting on nucleophilic substitution reactions, we have studied in details the mechanism of SN1 mechanism, SN2 mechanism, neighboring group participation in nucleophilic substitution reactions, and their stereochemistry also. Today we will be studying the nucleophilic substitution reactions of alcohols and ethers. So before we start with this, I would like to concentrate on the structure of alcohol. So if we look into the structure of alcohol here, what we find is that in alcohol, because of the oxygen, it induces polarization in both the bonds, that is the CO bond is also polar as well as OH bond is polar. Since these two bonds are polar, therefore alcohols are slightly acidic in nature because hydrogen has a positive charge. At the same time, carbon has a positive charge on it, so it should undergo nucleophilic substitution reactions. But the irony of the situation here is that OH is a strong base, therefore it is not a good leaving group, it is a poor leaving group. So our first objective or our emphasis today is going to be on how we can convert OH into a good leaving group. After we've converted this into a good leaving group, then what we find is that this can go normal SN1 reaction mechanism or SN2 reaction mechanism to undergo nucleophilic substitution reactions. Today we will be studying another new set of reactions, which is SNI reaction. So to start with this, what we find is normally if I am talking of an alkyl halide and I have to convert alkyl halide to alcohol, the reaction is quite simple. That is, we can do the reaction of alkyl halide with aqueous KOH because Cl is a weak nucleophile or it's a weak base and it is easily replaced with OH. But when we talk of conversion of alcohols to alkyl halides, we find it is a little difficult task because OH is a poor leaving group. So what we have to do now is to convert this into good leaving group. But before we do that, the different reagents which can bring about these halogenation reactions are concentrated HCl, HBr, that is halogen acids, or we can have inorganic reagents like PBr3 or thionyl chloride. Then depending also on the structure of the substrate, that is alcohol, if it's a tertiary alcohol, the order it will be most reactive, followed by secondary alcohol and primary alcohols. Then what we find that if we are discussing primary alcohols, then methanol is more reactive as compared to other primary alcohols towards this substitution reactions. So what we have to do is now let us look into these reactions in details. So what we find here is that is if we have to carry out this reaction, that is reaction of alcohol with Br, this reaction is not possible. That is, if I am trying to do the reaction with NaBr, this reaction is not possible because OH is a poor leaving group. So our first objective is going to be to convert this OH into a better leaving group. How can we do this? We can convert OH into a better leaving group by treating OH, alcohol, with a strong acid. When we do so, here a acid-base reaction takes place. O, because on oxygen there are lone pair of electrons, it can act as a base as well as a nucleophile. In this case, it is acting as a base and it undergoes acid-base reaction and we get a protonated alcohol. Now this protonated alcohol, in SN2 mechanism, what happens here is that this loses a water molecule. What happens here is that first of all we've converted OH into a better leaving group, which is H2O. Second, this group is more electron withdrawing as compared to OH. As a result, the positive charge on carbon increases, that is, carbon becomes more electrophilic and the nucleophile attacks from the backside as in SN2 mechanism, resulting in the formation of product. This was SN2 mechanism. Similarly, now if we have a tertiary alcohol, then a tertiary alcohol would prefer to go a SN1 mechanism, because in that case we will get a tertiary carbocation which is a stable carbocation. And secondly, SN2 mechanism is not possible here because the backside approach to the carbon would not be possible. So what we find here is that the oxygen reacts with H plus from hydronium ion to form a protonated alcohol. This is a fast reaction. And in second step, this protonated alcohol loses a water molecule to form a carbocation. Then this carbocation reacts with a halide ion to form this product. So if we look into some specific examples, then what we see is that secondary and tertiary alcohols undergo SN1 mechanism. Along with this, if the substrate is allylic or benzylic, then also it will undergo SN1 mechanism. So what we find here is that this reacts, the alcohol, tertiary butyl alcohol, reacts with HBr to form a protonated alcohol. So here we have converted OH into a good leaving group, which is water. Now when this group leaves, it gives us a carbocation, and Br minus, being a good nucleophile, a better nucleophile than water, will react with tertiary butyl carbocation to give us a product. This is an SN1 mechanism. So this was a normal SN1 mechanism. There was no rearrangement involved here because we got a tertiary carbocation here. But in case we have secondary carbocations in which there is possibility of rearrangement, then the carbocation formed will rearrange to give us a more stable carbocation through hydride shift or an alkyl shift, and then it will react further with the halide ion. So in such cases, the drawback of this reaction is that the expected product is generally formed in small quantities and the rearranged product is formed in major product. So what we find in this case is that if I look into this reaction, that is the 2-bromo 3-methylbutane, which should be the normal product, this is formed in small quantities, whereas the rearranged product is formed in major quantities. So what we find here is, like, if we do this reaction, which is it is because of the alkyl shifts, but I'll go back to a reaction which hydride shift was taking place. So what happens in first case is, that is the lone pair of electrons on oxygen react with H plus from acid to give us a protonated alcohol. This protonated alcohol loses a water molecule to form a carbocation. Now this carbocation is a secondary carbocation, and if we look into the structure, that at beta carbon we have a hydrogen which can shift as hydride, or we have a methyl group which can shift as a methyl shift. But what we find here is that in between the two cases, if a hydride shift takes place, then we get a tertiary carbocation as in here. So this tertiary carbocation is more stable than a secondary carbocation which was formed initially. This tertiary carbocation in a fast step, that is the next step, traps the Br and we get the product which is not the expected product. Second case in which again a rearrangement takes place through alkyl shift is, supposing if a hydrogen is not present on beta carbon, then in that case the carbocations will rearrange due to methyl shift. So what happens in this case, as in the previous example, that is OH reacts with H plus to give us a protonated alcohol, which then loses a water molecule to form a carbocation. In this carbocation, again methyl shift takes place to give us a tertiary carbocation, which then reacts with bromide to give us the product. So in all these cases, that is in SN1 reaction, what we find is that rearrangement in the substrate takes place to give us the final product. So sometimes we do not get the product that is expected. Till now we have discussed the reactions with HBr and HI. Now if we look into HCl, that is we are talking of the reactivity of halogen acids, then what we find is that HI is most reactive, followed by HBr, followed by HCl. So in case of HCl, Cl is a poorer nucleophile as compared to Br minus or iodine minus. So when we do the reaction with HCl, we have to use a Lewis acid, which helps in the cleavage of OH bond by converting it into a better leaving group. So what we find is ZnCl2 is a very good reagent for this reaction. It helps in the reaction. And what we find here is in most of the cases, if I am talking of a primary alcohol, then reaction takes place through SN2 mechanism. And as you know that HCl and zinc chloride are the basis of Lucas test. That is, this reagent is used to distinguish between tertiary, secondary and primary alcohols. That is, tertiary alcohols will give turbidity immediately with Lucas reagent, secondary alcohols after 5 minutes, whereas primary alcohols only on heating. So what we find is, how does this reaction proceed? So what happens in this case is that zinc chloride, being a Lewis acid, forms a bond with lone pair of electrons on oxygen, resulting in formation of a complex. In doing so, it converts OH into a good leaving group, which has been shown by red in the reaction. So what happens here is, in an SN2 mechanism, the leaving group, the departure of the leaving group and the attack of the chloride on the alkyl group are taking place simultaneously. So in this case, zinc chloride has acted as a catalyst in the reaction. So what we find is that if the alcohol is primary, it undergoes reaction by SN2 mechanism. If the alcohol is secondary or tertiary, it undergoes SN1 mechanism. But what we find is that when it undergoes SN1 mechanism, then the drawback of the reaction is that the reaction is accompanied by rearrangement. That is, we get the products which are not desirable. So in order to get only the product that we desire, we can use other reagents also to convert alcohols into alkyl halides. Two very good reagents are PBr3, which converts alcohols into bromides, and thionyl chloride, which converts alcohols into chlorides. The reaction mechanism here is very little different, because here carbocations are not formed as intermediates, so rearrangement does not take place. And the reaction proceeds through formation of complexes. And these inorganic reagents will convert alcoholic groups into good leaving groups under mild conditions. So what we find here is that is if I take a secondary alcohol and treat it with phosphorus tribromide, we are getting 3-bromopentane. So in this case what we find is that PBr3 is a very good reagent because one molecule of PBr3 reacts with 3 molecules of alcohol. So it is a very effective brominating agent. Not only this, since the rearrangement is not possible here, we get a very good reaction. But what we find here is that the reaction mechanism is little different. In this case, alcohols are acting as nucleophiles. Normally in most of the reactions, alcohols are acting here as substrates. And in this case, since the phosphorus is attached in phosphorus, it is attached to 3 bromide groups, so it is electron deficient. So here the alcohol acting as a nucleophile reacts with phosphorus and converts into protonated alkyl dibromophosphite, which is a good leaving group. So what we find here is that the function of PBr3 is double. That is, first it converts OH into a good leaving group, and secondly it is providing Br minus, which then acts as a nucleophile in the next step. What happens in the second step is that a leaving group, which the OH group which has been converted into a good leaving group, leaves, departs, and at the same time Br acts from the opposite side in SN2 mechanism to give us the alkyl bromide. So in this case no rearrangement has taken place, and then HOPBr2 can now react with other 2 molecules of alcohol to give us alkyl bromide. So the yield is also high. Similarly, alcohols can be converted to iodides by doing reaction with phosphorus iodide. But since phosphorus iodide is unstable, it is highly reactive. So it is prepared in situ by doing reaction of iodine with red phosphorus, and then the mechanism of the reaction is similar to what we have discussed with PBr3. Another very interesting reaction, and which is very practical also, that is the reaction of alcohol with thionyl chloride. What is different about this reaction is that is when we do the reaction with thionyl chloride, there the reaction is accompanied by retention in configuration, whereas if the reaction is done with thionyl chloride in presence of pyridine, then reaction is accompanied by inversion. So if inversion is taking place, we say, okay, fine, it is an SN2 mechanism because inversion is the characteristic property of an SN2 mechanism. But how do we explain this retention? That means some neighboring group participation is taking place. We do not find any neighboring group here which can participate in first intramolecular nucleophilic substitution reaction. That means the reaction mechanism is different. Here we will be discussing SNI mechanism, that is internal nucleophilic substitution reaction mechanism. So the first case what we see was a very interesting example which was given by Walden. What did Walden do? Walden did the reaction of malic acid with PCl5, where he found that the product which was chlorosuccinic acid, there was inversion in configuration. Whereas when he did the reaction with thionyl chloride, he got a product in which there was retention. So after Walden, we also call the SN2 reactions in which inversion has taken place as Walden inversion. So how Walden inversion we can explain on the basis of SN2 mechanism, but the retention in configuration cannot be explained by Walden reaction, by SN2 mechanism. So now if we look here and we say, supposing we propose, it would come to a mind maybe this is the mechanism of the reaction, that is the OH acting as a nucleophile, oxygen acting as a nucleophile reacts with sulfur, which is an electrophilic site, to give us a chlorosulfite intermediate, which then loses a chloride ion, and then this chloride ion attacks from the backside, giving us the product. So in this case, what we find is that there is inversion in configuration. But this is not possible, because if there is inversion in configuration, that means there should be a backside attack is not possible, since there is no inversion in configuration. And there is no pentavalent state also formed, intermediate also formed. It cannot be SN1 mechanism, because there is no racemization in the reaction that we are observing. So that means this mechanism is wrong. There should be something else. So the proposed mechanism for this is that in this case, again, we have to keep two things in mind. That is, this malic acid, in malic acid, the lone pair of electrons on oxygen of the hydroxyl group are acting as nucleophilic site, and it attacks the sulfur. So now what is the function of sulfonyl chloride here? It is first of all converting OH into a good leaving group. Second, it is providing us with the nucleophile, which is chloride. So what happens in first case is that O acts as a nucleophile and reacts with sulfur to form a chlorosulfite ion. So what happens in chlorosulfite is that this chlorosulfite here, this Cl minus goes, abstracts up H proton from here, and it forms into the next substrate here, which is again in this it has not parted, this forms a intimate ion pair. What I mean by saying intimate ion pair is that this has not parted from here, but this is still here. So what we find is that the Cl has left. So we have an intimate pair here. Here the Cl attacks from the same face from which the nucleophile, the departing group has left. So there is retention in configuration. And at the same time, SO2 is also departing and HCl is also departing. So what we find here is that chloride attacks carbocation on the same face of the intimate ion pair as the face from which it has left. So there is retention in configuration. This type of mechanism is called as nucleophilic substitution reaction with internal return. Now if we look into the reaction of alcohol, so what we find here is, that is, when we talk of this alcohol, it reacts with thionyl chloride to form a sulfite, chlorosulfite. This chlorosulfite then loses the H plus to the solvent molecule to form an intimate pair. So in this intimate pair, the chloride ion is reacting from the same side as the intimate pair had left. So what we have here is that the attack has taken from the same face and there is retention in configuration. Now if we look into the second mechanism in which the reaction has done in presence of pyridine, then what we find in this case is that the reaction is accompanied by inversion in configuration. How does this happen? In this case, the first two steps are the same, that OH, the O is acting as a nucleophile, it reacts with sulfonyl chloride to form a chlorosulfite intermediate. The reaction now differs from here. In this case now, pyridine acts as a nucleophile through lone pair of electrons on nitrogen. It comes and makes a bond with sulfur. So when it forms a bond with sulfur And at the same time, what we find is it forms a intermediate here. And in the next structure, what we find in the intermediate is that the oxygen is given out, and the chlorine ion is given out, and we get an intermediate here. Now what we find is that in this case, this is blocked. This site is blocked here. Since this site is blocked here, what we find is now Cl cannot attack from the same site. It goes and attacks from the back side, since it is being offered steric hindrance on the same face from which it has left. So now the attack is from the back side, resulting in formation of a product with inversion in configuration. Pyridine is also regenerated in the same type, and SO2 is liberated. So what is the bottom line? The bottom line of this reaction is that if we treat malic acid with SOCl2 alone, then there is retention in configuration, whereas when we do the reaction in presence of pyridine, then nucleophilic substitution reaction SN2 reaction takes place. The intermediate formed is common till chlorosulfite intermediate. After that, we get an intimate ion pair which is closely held in space, and in this intimate ion pair, chlorine attacks from the same face, resulting in retention in configuration. Whereas in case of pyridine reacts with sulfur, blocking the inset of chlorine from the same side. Hence chloride ion has to attack from the opposite side, resulting in inversion in configuration. So now what we'll do is, what I have done here is I have summarized the reactions and the reagents which help us in converting alcohols to alkyl halides. So one very useful reagent is HCl, and in all these cases it will work with all the alcohols. If we are looking into primary alcohols, then the mechanism is SN2, and secondary and tertiary alcohols will undergo SN1 mechanism. Thionyl chloride is a very good reagent because the side products formed here are HCl and sulfur dioxide, which are emitted from the reaction, and it is best for converting methanol and primary and secondary alcohols via SN2 mechanism. If we have to convert alcohols into bromides, then HBr is a very good reagent because it can work with all the types of alcohols. Secondary, tertiary, benzylic and allylic alcohols will undergo SN1 mechanism, whereas methanol and primary alcohols will undergo SN2. PBr3 is again a very good reagent because in this there is no rearrangement, no carbocation formation, and this is good for methanol and primary alcohols through SN2 mechanism. And again we can use HI to convert alcohols into iodides, and it is useful for all the types of alcohols. So in these cases we had convert alcohols, the OH group, into a good leaving group by treating them with acids, like that is with H+, or we had converted OH into a good leaving group by doing the reaction with Lewis acid ZnCl2, or with PBr3 or thionyl chloride. Now we can carry out alcohols, we can convert alcohols into alkyl halides also by converting alcohols into some other good leaving groups. Other good leaving groups to which alcohols can be converted are tosylates or triphlates, because tosylates are bases of very strong acids. So what we do here is, that is, we convert alcohol into alkyl tosylates. So these are generally made up of two parts. The first is the R part, alkyl group, which is coming from the alcohol, and the other is the tosylate group, which comes from para-toluene sulfonate. This tosyl group is a very good leaving group. So, and it is normally abbreviated as TS. So when we write the structure of alkyl tosylate, it becomes ROTS. So what are we doing in this case is, in case of alcohols, we are converting the group OH into a tosylate group, which we put in a bracket here, which is a good leaving group. And this tosylate group is abbreviated as tosyl group. And when we write the structure of alkyl tosylate, we write it as ROSOO and a tolyl group, which is abbreviated as ROTS. Now what do we do? So what we do here is, alcohols are treated with para-toluene sulfonyl chloride in presence of pyridine, and in this process we convert OH, which is a poor leaving group, into a tosylate group, which is a good leaving group. Tosylate group is a good leaving group because it is a base of a strong acid, which is para-toluene sulfonic acid. So what we do here is, first we treat alcohol with para-toluene sulfonyl chloride, when we will get we are converting OH into a good leaving group. So since in this case the reaction is not taking place at the carbon, so what we find is that the stereochemistry, or when we will discuss the stereochemistry of this reaction, it does not change. The bond cleavage is between O and H bond. So in the next case, if I look into it, as I said, that the stereochemistry does not change. If we compare, or if we take the structure 2-butanol and we are doing the reaction with para-toluene sulfonyl chloride, so what we find here is that O acts as a nucleophile here, the lone pair of electrons on oxygen act as a nucleophile here, and they react with sulfur. And we get a tosyl group here, alkyl tosylate group here, in which we have a good leaving group. Since the bond between carbon and oxygen is not breaking, therefore the configuration at this carbon is retained. That is, we will get S isomer from S-butanol. Now in the second step, when we do the reaction of this with, we make it undergo nucleophilic substitution reaction, it generally undergoes nucleophilic reaction with inversion in configuration, which we will be discussing very shortly. Now these groups, tosylate groups, are as good leaving groups or are better leaving groups than halogen atom. So therefore they can undergo both nucleophilic substitution reactions as well as beta elimination reactions as alkyl halides do. So generally when we treat alkyl tosylates with strong nucleophiles, it follows SN2 mechanism in nucleophilic substitution reactions and E2 mechanism for elimination reactions. So what we find here is that in first case, what we've done here, we have converted this tosylate, the alcohol, into tosylate group, and then when we treat this ethyl tosylate here with a strong nucleophile, it can undergo SN2 mechanism by a backside attack, and what we get here is a ether, which is a substitution reaction. But at the same time, if we change the nucleophile and we change it into tertiary butyl butoxide, then what we find here is that elimination predominates here, and we get here is an alkene. So depending upon the reaction condition, if the nucleophile is strong, moderately strong, it is not a bulky nucleophile, then we get a substitution, whereas if it is a bulky nucleophile, then elimination is favored. And since the reaction mechanism is SN2, then what we find is that the reaction, the nucleophile will attack from the opposite side here, replacing the tosyl group, and what we get here is the product here is inverted product. There is inversion in configuration at the stereogenic center. So if we summarize this, we can say when we are talking of reaction of alcohols, this takes place in two steps. In the first step, we have converted alkyl into a tosyl group. Here there is retention in configuration if the starting compound is optically active, and then when we do the reaction with nucleophile, and then we treat it with a nucleophile, which is a backside attack, and we get the product. So that means step number 1 is the formation of the intermediate of a tosylate in which there is retention in configuration. So what we've done in this example is we've started with a cis isomer. So when we are treating it with tosyl chloride in presence of pyridine, we are getting a cis isomer. But in reaction number 2, that is the step in which there is nucleophilic substitution reaction, here the attack will be from the backside since it is an SN2 mechanism, and there is inversion in configuration. That is, we are getting a trans isomer from a cis isomer. So the overall reaction results with inversion in configuration. So now if we summarize the reactions between nucleophilic substitution reactions and elimination reactions, so we know that if we are doing the reaction of an alcohol with concentrated sulfuric acid, then concentrated sulfuric acid is a dehydrating agent, or with POCl3 in presence of pyridine, then we will get an alkene. If we do the reaction with an alkyl halide or a thionyl chloride or phosphorus tribromide, then we get an alkyl halide. And this is a very important intermediate, because with this alkyl halide, if this is treated with a strong nucleophile, we may get a nucleophilic product, a substituted product, or it may result in the formation of an alkene. And if we do the reaction again with tosyl chloride in presence of pyridine, first we'll get a tosyl derivative, which is then capable of undergoing both nucleophilic substitution as well as elimination reactions. So alcohols are very interesting group of compounds, but they cannot undergo nucleophilic substitution reactions readily. So our aim is going to be to convert it into a derivative or a compound so that OH becomes a good leaving group, that is, we convert it into an alkyl halide or a tosylate group or a triplet group, and then we can carry out a number of synthetic reactions which are of use in everyday life. Not only this, what we find is we can also prepare ethers from alcohols. How do we do this? There are two possible mechanisms. First is by intermolecular dehydration of alcohols. This has a number of drawbacks. And then the second, which is a very important reaction, is Williamson's ether synthesis. We'll be discussing both these reactions one by one. So in first case, what we see is that if we treat alcohol at 140 degrees, then it will give us ether. So in this case, what happens is one molecule of alcohol acts as a nucleophile, and the second molecule of alcohol acts here as a substrate. So the first molecule of alcohol first reacts with H+ from acid to form a protonated alcohol. To this protonated alcohol, then the second molecule of alcohol reacts here through lone pair of electrons on oxygen, that is, it acts here as a nucleophile. And the protonated alcohol here is acting here as a substrate. The attack of the nucleophile and the departure of water as a leaving group is taking place simultaneously, resulting in formation of protonated alcohol. And in the second step, this protonated alcohol loses its H+ to the water molecule to form a ether molecule, to form ether. This reaction is quite good, but if the reaction temperature is, say, elevated to 180 degrees Celsius, then what happens is that this alcohol will undergo beta elimination, and what we get here is an alkene through E2 mechanism. And if we think of preparing ethers from secondary and tertiary alcohols, then it is a quite difficult task, because what we find is that it will undergo elimination through E1 pathway, that is, we'll get a carbocation intermediate, and when we get a carbocation intermediate, then the possibility is that that carbocation may undergo SN1 mechanism or SN2 mechanism. And what we find here in most of the cases, that the E1 mechanism predominates and we get alkene as the major product. So what we find is that during intermolecular dehydration of alcohols to form ethers is a difficult task, because what if we by chance we take two ethers, that is I want to make a mixed ether, then in that case we will get a mixture of ethers. That is, if I take ethanol and methanol, I will get a mixture of diethyl ether, dimethyl ether, ethyl methyl ether, along with some little amount of alkene also. And if we take tertiary alcohols, then in that case alkenes will predominate. So Williamson then proposed a mechanism, an important rule for preparation of unsymmetrical ethers through SN2 mechanism. So here also, if by chance we are taking tertiary ethers, we will be facing the same difficulties that we are facing in SN1 for the mechanism that we followed in intermolecular reactions, but the possibility would be less. So now when we talk of Williamson synthesis, so what do you think could be the mechanism? So we can say we can take a primary alkyl halide and the alco oxide, which is acting here as a nucleophile, can be a tertiary one also. So what we do here is we take the alco oxide as tertiary or secondary, or if we want a highly alkylated ether, then alco oxide is taken as tertiary and alkyl halide or alkyl sulfonate esters as primary. When we are doing the synthesis, please keep this in mind. By chance, if we take alkyl halides as secondary or tertiary, then eliminated product will be formed. Then in second case, what we do is we convert the alcohol into alco oxide by treating it with sodium hydride, and what we can do is we can use the solvent of the same alcohol of which we are taking alco oxide, or we can also use other polar aprotic solvents like DMS. So they greatly help in SN2 mechanism. So now if we look into ether synthesis here, what we've done is we've taken sodium alco oxide and we are treating it with alkyl halide in DMSO as a solvent. This is a mechanism, this will follow SN2 mechanism and give us an ether. So here what we see is that the solvent is playing an important role. That is, if we take butanol as a solvent, which is the parent of sodium butoxide of the same alco oxide, then the yield is 60%, whereas if we take DMSO as the solvent, then the yield is 95%. So that means DMSO is a better solvent than butanol. Aprotic polar solvents, please remember, favor SN2 mechanism. Second, again we've taken another example in which we've made a cyclic ether by using the same procedure. So now if we look into this mechanism, now let us look into the mechanism of the reaction. So what we find here is that if I am taking tertiary butoxide and treating it with ethyl iodide, we are getting butyl ethyl ether plus NaI. So what happens in this case is, and the second example that we have discussed today is, that is we are taking benzyl chloride and treating it with sodium isopropo oxide when we are getting benzyl isopropyl ether in 84% yield. So what is the mechanism of the reaction? As I said in the beginning, our first objective should be to take alkyl halide as a primary, not secondary or tertiary. If we need to have a secondary or a tertiary alkyl group, then in that case it should come from the alco oxide. So what we have here is we've taken benzyl chloride as the primary and then we've taken sodium propo oxide and we are getting a ether here. What is the mechanism of the reaction, or how do we get the reactants? For getting the reactants, we have treated benzyl alcohol with HCl, converted into benzyl chloride, and we've treated isopropyl alcohol with sodium to convert it into sodium isopropo oxide. And then we react these two to get the ether that we desire. What would happen now? Imagine, I've been telling you right from the beginning that the alkyl halide should be primary. If the alkyl halide is secondary and alco oxide is primary, what do you think will happen? In this case, elimination will take place because we have a beta hydrogen. That is, bromine will be removed from alpha carbon, and then hydrogen will, as proton will be removed from beta carbon, resulting in formation of an alkene. So whenever you're doing the reaction, preparation of ethers, please remember that the alkyl halide should be primary with less consequences for it to undergo elimination reactions, whereas we can take alcohol as secondary or tertiary, that is the alkoxide ion. Not only this, we can also modify a substrate and form cyclic ethers by intramolecular Williamson's ether synthesis. In this case, we take haloalcohols as starting point, and these are also known as halohydrins. Like, what are halohydrins? Halohydrins are those compounds in which OH and the halogen atom are present in the same molecule. So in this case, first what happens is that the OH comes and reacts with H+. It abstracts this H+, converting this into an alco oxide ion. So in this case, the alco oxide ion undergoes intramolecular nucleophilic substitution reaction, and we get a cyclic ether. The chances of OH reacting with a carbon bearing the Br is less because the rate of reaction of intramolecular reaction is more, and secondly, if we take the substrate in a diluted form, then also the reaction would be faster. So again, I have done a number of syntheses here involving intramolecular Williamson's ether synthesis, and what we find is that we can even prepare epoxide, that is, epoxides are rings which are having 3 rings in it, 3 atoms in it, 2 carbon and 1 oxygen, can also be prepared by this method. So now we'll quickly go to the next slide, and in this slide what I have shown here is, like, if we are talking of intramolecular ether synthesis, then the point that we have to keep in mind is that these should be in NT conformation. The molecule should be in NT conformation. Why is it so? Because the O minus, which is acting as a nucleophile, as we can see in this reaction, reacts from the backside. If it was in the gauge conformation, this would not have been possible. So what happens here is, that is, the bond formation and the leaving group is departing in the same step. So the basic conformation that we need here is the NT conformation, which results in the formation of epoxide. Next very important class of reactions, nucleophilic substitution reactions, are cleavage of ethers with acids, strong acids. Now we know ethers are not very reactive because they are made up of an alkyl group which is not reactive. It only undergoes halogenation by free radical mechanism. And second, we find is that oxygen here is also not a very good leaving group. So what we have to do here is, first point is to convert this oxygen into a good leaving group. This we can do so by treating it with strong acids like HI, HBr. So what happens, and then after it has been converted into a good leaving group, both the oxygen and the carbon bonds will break to give us 2 molecules of alkyl halide. So 2 bonds are broken and 2 new bonds are formed in this case. So what we find here is that if I am treating methyl ethyl ether with HBr, then we will get methyl bromide and ethyl bromide. And if we are treating methyl tertiary butyl ether with HI, we are again getting tertiary butyl iodide and methyl iodide. Now the question to be considered here is, if we have an ether of the type which is coming on your slide, then here two possible mechanisms are possible. That is, at the methyl group, the mechanism will be SN2, that is the bond will cleave here by SN2 mechanism. Whereas if I look into the tertiary butyl carbon, then there the mechanism would be SN1 mechanism. So let us take this into more detail. So if I look into this, what happens in the first step is, as you know, as I've said in the beginning, we will have to convert this O into a good leaving group. It is not a good leaving group. So methox O reacts with H here in the form of an acid-base reaction to give us a protonated ether, in which the methanol group now becomes a good leaving group. So what we get here is a carbocation. This is following an SN1 mechanism here, and then I minus reacts with this carbocation to give us a tertiary butyl iodide. Whereas if we look into the second part, methanol, now we are doing the reaction with excess of HI, then here this methanol will react with H plus to give us a good leaving group. Here in the second step, what happens is both the reactions, that is the attack of the nucleophile and the departure of the leaving group, is taking simultaneously through SN2 mechanism, and we get methyl iodide. So what we find is that if the ether is unsymmetrical, then it can undergo SN1 as well as SN2 mechanism in the same molecule. Here I have taken examples of aromatic ethers. So if we take phenyl ethyl ether, so what we find here is that the mechanism is through SN2 and we get ethyl bromide. Here we do not get phenol. That is, the phenol is not converted into chlorobenzene here, because as we know, we've discussed this earlier on also, that the lone pair of electrons on oxygen interact with the pi electron cloud of the benzene, resulting in partial double bond character between C and O, and the cleavage of this bond becomes difficult. Whereas in second case, what we find is, again this is a aromatic ether, then what we find here is this will undergo SN1 mechanism, because the benzyl carbocation formed is resonance stabilized. So at this point the mechanism would be SN1, whereas when we look at the ethyl part, there the mechanism will be SN2 mechanism. So we can cleave ethers into the iodides by treating them with different reagents like with HI and HBr. So again here in these examples, again I have discussed the mechanism in more detail. So we can afford to skip these reactions, and we will now go on to acid catalyzed cleavage of cyclic ethers. So what we find similarly, if we treat a cyclic ether with HI, again we will get a diiodo product, and the reaction mechanism is similar, that is it undergoes mechanism through SN2 mechanism. That is, first the lone pair of electrons on oxygen will react with proton to form a protonated ether, then I minus attacks at the next carbon to give us a iodo alcohol, and then it reacts again with second molecule of HI to convert into a diiodo product. Now what I want to tell you further is, not only acids but even some strong nucleophiles can bring about this reaction. So in short, to summarize this, what we see is that we have cyclic ethers, that is epoxides, and we do the reaction in presence of a strong nucleophile, then also the ring opening takes place, and we can bring about ring opening with HCl also. But what we find here is, what I want to stress here is, that if the ether is unsymmetrical, then what happens is, that is, if we are doing the reaction in presence of a strong base, then the reaction takes place at a carbon which is less substituted. because in this case it is following SN2 mechanism. Whereas if we do the reaction with an acid, then in that case nucleophilic substitution reaction takes place at that carbon which is more highly substituted. So we say that these reactions are regioselective, that is when we are doing the reaction in presence of a strong nucleophile, then reaction is taking place at that carbon which is less substituted, whereas when we do the reaction with an acid, that is we bring about the cleavage with an acid, then the reaction is taking place at that carbon which is more highly substituted. As usual, when I summarize my reactions, I will just take quickly one example of a biological system. So what we find in a biological system, we've heard that now we are switching to TBX, that is toluene benzene xylene mixture for automobiles, which is an unleaded petrol. But have you ever thought that the benzopyrene, the things which come out of it are carcinogenic, or the compounds that we use in a lab are carcinogenic? When we inhale these compounds, they undergo oxidation in liver and to form a EPO oxide. And surprisingly, this EPO oxide reacts with the nucleophile, that is with DNA and other enzymes in our body, to give us open chain compounds which are carcinogenic. So nucleophilic substitution reactions play a very important role in biological systems also. So with this, I'll wind up my lecture today, and maybe we will continue with this next time, or we may even switch to isomerism. Thank you.
With this note, thank you, ma'am. Thank you once again for giving us a very productive session. Dear friends, if you have any queries or if you want to give your feedback regarding this particular lecture, then you can mail us at info.cc@nic.in. We would be waiting for your feedback. Till then, take care. Goodbye. Thank you, ma'am.
Thank you so
very
much.